Okay, so good afternoon, ladies and gentlemen. Today I have a big pleasure to introduce Sourav. He's nowadays in the Mathematical Institute in Academy of Science, and let me say a few words about him. He did his master in Data Institute in Bangalore, then he moved to France, and he did his PhD with two supervisors, with Silva and with Jean-Pierre Raymond. Then he moved as a postdoc to University of Würzburg. He was postdoc of Dr. Anja Schlemmer-Kempfer. And after three years, more or less, he moved to Prague, and he's now from January, February, he's in our institute. And today he will speak about a multi-component full structure interaction problem. Please.
Thank you, Sourav, very much for the introduction, and thanks all of you for being here. So I'm going to talk about a multi-component fluid structure interaction problem involving compressible fluids. Talking about your fluid structure interaction problems, we see several examples every day around us. The first one is a bridge moving due to wind, and wind is compressible, air is compressible, and this bridge is like elastic structure. So the first one is an example of a compressible fluid structure interaction model. And then there are other examples like flow of blood through arteries. Blood is incompressible viscous fluid, and the wall of our arteries is like elastic membrane. So this can also be considered as an example of a fluid structure interaction problem involving an incompressible viscous fluid with elastic structure sitting at the boundary. And then there can be other examples, and then there can be many more, like the motion of a submarine underwater. This seawater is again incompressible, so this is also an example of a fluid structure interaction problem involving incompressible fluid and the solid structure. But today I'm going to speak more about the first one, a compressible fluid structure interaction problem with elastic structure sitting at the fluid boundary. But before I go into the main part of the talk, I would like to talk a little bit about compressible fluids and the classical theory of weak solutions. And I'm sorry, probably most of you already know this theory, but I want to talk about this for maybe someone who wants to know. So the first few slides are devoted for this classical weak existence theory of compressible Navier-Stokes equation. Especially, I wanted to talk how the adiabatic exponent influences the weak existence theory for compressible fluids. So here it is on weak existence result, which is quite classical for compressible fluid flow. Yeah, so when you talk about compressible Navier-Stokes, let's say we have a torus, so we can have a boundary, and it's constituted of two equations: the continuity equation, which is the time derivative of rho. Rho is the density, and divergence of rho u, u being the fluid velocity. And then we have the momentum balance equation, which is given by the time derivative of the momentum plus the convection term, divergence rho u times u, and the viscosity terms, mu and lambda being the lambda coefficients, plus the pressure, which is a function of the fluid density. Now, the pressure can be given by a monotone function of the form rho to the power gamma, for gamma greater than 0, which we call the adiabatic exponent. And because we are interested about speaking about the weak solution of compressible Navier-Stokes, here we have the weak formulations. It's just multiplying both the continuity equations and momentum equations by some smooth test functions, integrate by parts and shift all the derivatives to the test function to give these weak formulations. So it's not, it's not very complicated to compute what the weak formulations look like. And then this system comes with natural energy, which is given by the time derivative of the integral over our torus of this quantity, which is the energy density times u square, which comes from the convection part, and rho to the power gamma, which comes from the pressure, and the dissipation, which is given by this thing with mu and lambda being the lambda coefficients. And now, whenever in PD we talk about proving existence of weak solutions, we first discretize our PD and try to show try to show an energy balance of this kind, and from that we extract a weak convergence subsequence, use some kind of abelians to extract strong convergence subsequence, and try to pass limit in the nonlinear terms to produce a solution of our PD. And for compressible Navier-Stokes, to pass limit in the convection part, it's not so hard, not so delicate. It can be done by a priori estimates and strong convergences due to abelians kind of argument. But then, and also the viscosity terms, they're just linear, so there is no problem passing limit there. The most difficult part is, of course, to find some compactness of the pressure, and there are two theories. One due to PLDons, and second one due to Friedreich. So I'll talk a very little bit on that, just to have an idea of the analytic exponents we need for the proof of weak solutions. So first of all, why this difficulty of the pressure, compactness of the pressure arises? Simply because from the energy, what we have is the density raised to the power gamma. It's bounded in L infinity L1. So we cannot simply extract a weakly convergent subsequence. And what we need to do is to prove a little bit of more integrability for density. And then we can we'll be able to extract a weak convergent subsequence of our pressure. So roughly, very roughly, the idea is to use a test function of the form Bohovsky operator operating on rho to the power theta. And what is Bohovsky operator? Formally, it's the inverse divergence. So in other words, it's divergence operating on Bohovsky rho to the power theta is just rho to the power theta. And there is some extra term which I use to nullify the integral actually. And if we use this Bohovsky operator as a test function in a momentum equation, specifically from the pressure term, where we have the pressure times divergence of phi, we get a contribution of integral rho to the power gamma plus theta. And after a long calculation, what we can find that this thing, rho to the power gamma plus theta, its integral is bounded. And for compressible fluid, this extra integrability exponent, theta, is really not so big. But if you have gamma greater than 3/2, this theta, depending on gamma, can be given by 2/3 gamma minus 1, which means if we have gamma is equal to 9/5, this theta over 9/5 is 1/5, giving that rho is a square integrable function. So the whole idea of using this Bohovsky operator is to prove our extra integrability of the density, and a very small improvement over the integrability of rho. So it's now gamma plus theta. And now we can extract a subsequence because we have a bit more integrability than L1. We can extract a weakly convergent subsequence of the pressure converging somewhere. We call the limit as pressure bar, overlying the pressure, but we still don't know how to identify this limit. So what we have is just there exists a weak limit for this pressure, but we still need to identify this limit, and the steps are to prove either strong convergence or almost everywhere convergence of this density sequence. Now, to identify this limit, it's a bit complicated argument. I'm not going to detail that, but there are too many ingredients, of course. One is the renormalized continuity equation, and the second is the role of this quantity called effective viscous flux, which I mean, I'm not going to explain the role, how it's used to prove the compactness of density, but roughly the idea is I mean, this quantity, pressure minus divergence U, enjoys a better compactness compared to the pressure and divergence U, these two quantities individually. And what is renormalized continuity equation? And I'm going to comment a little bit on the renormalized continuity equation because it's also a very important part for our analysis, the multi-component fluid, which I'm going to speak in a while. So to speak about renormalized continuity equation, we first start with the formulation of continuity equation, which is the integral over the entire space-time cylinder of the of this density times the transport of the test function equals the integral of the density times test function at final time minus the integral at initial time. And we are interested to find an equation solved by rho, or not rho, but a function b rho, where b has some properties like gradient of b is bounded and b0 is 0. And we are interested to find the equation solved by this b rho, which is like a continuity equation, but a little different. I mean, in very informally speaking, it's just chain rule of derivatives. So what we have, the renormalized continuity equation, it looks something like this: the integral over the entire space-time cylinder, b on rho times this transport of test function minus some quantity. It is there because simply, as I was saying, renormalized continuity equation is informally the chain rule of derivatives. So we have some extra terms here, and at the right hand side we have the integral of b rho times the test function at the final time minus the initial time. So for the proof of the renormalized continuity equation, from the continuity equation, if you have the velocity field in L2 W12, one needs the density to be in L beta, so where beta is greater or equal to 2. So the integrability of density, if the density should be at least square integrable, which means that if our adiabatic exponent is greater than 9/5, then because of this slight improvement due to Bohovsky, we actually have the square integrability of density. So here comes the role of this exponent 9/5 in the weak existence theory of compressible Navier-Stokes equation, and it was proved by Pierre Lyons that because he completely relied on this existence of this kind of proof of renormalized weak solution using free commutator argument, which uses the square integrability of density. So he was able to prove that if the adiabatic exponent is greater than 9/5, then the compressible Navier-Stokes equation admits of a weak solution. This result was improved by Edward Feiereisel to include gamma greater than 3/2, and it was possible because I mean, Feiereisel said that okay, you don't actually need the square integrability of density, but what you need, he proved something like oscillation defect of the density. So even though your density is just bounded in L2, your oscillation defect of density is bounded in a much better space. So you could use that to improve the result to gamma greater than 3/2 for the existence theory of compressible Navier-Stokes equation. And okay, this was from the first part. I wanted to talk a little bit about the existence compressible Navier-Stokes. The next part is on our work, multi-component fluid structure interaction problem. It's a joint work with Sarka and Martin. So to talk about this model, we first write down the modeling assumptions. So what we do, we consider flow of a viscous compressible two-fluid model with the pressure law depending on both the fluid densities. And there is a quarter type cell located at the fluid boundary. And there is a simplifying assumption, like most of the articles in the literature, if not all, the cell moves only in the normal direction to the reference domain. And here by reference domain, I mean, whenever you want to, we want to describe the dynamics of a structure, it's always done in Lagrangian coordinates with respect to fixed reference configuration. For fluid, it's different, it's more or less Eulerian coordinates we do use. And then the fluid structure interface is supplemented with adherence type condition. By adherence, I mean the fluid sticks to the plate. So whenever they move with the same velocity. There is a continuity of fluid and solid velocities at the interface. This is more or less the model you consider. I mean, it's roughly the picture of the model you consider, where you have the fluid in this moving domain, omega eta t. Eta is the displacement of the quarter cell sitting at the fluid boundary, and nu is the normal to the reference configuration, where nu, depending on eta, is the normal to the moving cell. Yeah, so if you want to write down the model in a mathematical way, it looks like that. First of all, the continuity equations. So you have two densities. So two continuity equations, one corresponding to the first density rho. The next one concerns the second density z, and u is the velocity. So there is only one velocity and two densities involved. And then there is the momentum equation, momentum balance, where it's given by the time derivative of the sum of two densities times u. This is the convection, I mean, involving the sum of two densities. On the right hand side, you have this term with the stress tensor of the fluid, and the pressure, again, is a function of two densities, rho and z. And for the dynamics of the structure, it's I mean, equation second order in time and fourth order in space. So and eta is the structural displacement, and k is the quarter energy. It's non-linear and non-convex. So I'm going to comment a little bit about that in a couple of slides. And the structure moves because there is this I mean, force due to the fluid which acts on the structure. So it's like F, but simplifying assumption, it only moves in the normal direction, so F in the direction of the fixed normal nu, where F is the force of the fluid on the structure, which is given by the stress tensor minus the pressure, and then this fluid and the structure are defined in different domains because of this Lagrangian and Eulerian coordinates. So there should be a way to connect these two coordinates. And this is exactly done by this function phi eta, where phi eta is nothing but eta, the displacement, times, I mean, in the direction of nu, that normal to the fixed configuration. And then, because if you are using this function phi eta, so we should also include the Jacobian of the transformation, which appears here, determinant of d phi eta. And this is the expression of the stress tensor with two viscosity coefficients, which are constant, mu and lambda. And then we have the continuity of the velocities at the interface, which is given by the fluid velocity at the interface equals the structural velocity in the normal direction. And it is because of the assumption that the fluid adheres to the plate. And then everything is supplemented with initial conditions for the two densities, the part concerning the momentum and the structural displacement and the structural velocity. So of course there should be something like at time 0, which is missing here. And then there is some assumptions on the pressure we consider, and also there is some assumptions on the initial densities. So I mean, there is already some result Newtonian propellant structure, and our assumptions on the pressure are kind of in line of the assumptions of Newtonian propellant. So here are some assumptions. The initial densities, rho 0 and z0, they're comparable. So this is the condition which tells that they are comparable. Z less is equal to constant times rho, and integrator equal to some constant, some other constant times rho. But both of these constants are positive. And second one, even if we don't have explicit structure of the pressure, we have this assumption on the pressure which says the pressure from the above is bounded by a quantity of this form, rho super gamma plus z super beta plus 1. Of course, this part means whenever you have some integrability of this quantity, you can at once get the integrability of the pressure. And then there is another assumption. The pressure from below is bounded by rho super gamma plus z to the power beta minus 1. So which does the opposite solve, which means if we have some integrability of this pressure, we can extract the integrability of these quantities rho super gamma and z to the power beta from that. And the third assumption, which says that the pressure is Lipschitz in the second component, and the Lipschitz constant is bounded by some power of the density. So we'll see in a few more slides why this assumption is so important for us. And the final assumption, which says that the pressure can be decomposed into two parts. One, the first one, the monotone part, and the second one, which is rather smooth. So it's the assumptions are on R, like R is a C2 function with compact support. Now there might be it might seem a bit surprising that instead of writing P as a function of rho and Z, we have replaced Z by this quantity rho S, where S is nothing but this quotient Z by rho. So at this moment, I cannot explain why. I mean, we want to write it this way, but it will again be apparent from a few more slides that the role of this quotient quantity is. Okay, now those are few assumptions on the pressure, but we can have a typical example on the pressure which satisfies those assumptions. The pressure is of the form rho to the power gamma plus z to the power beta plus some term Fi, where the Fi's are the product of powers of densities and some assumptions on these powers, which makes these products integrable. And I assume here that the Ci appearing here are positive, which makes this pressure monotone. But even in some cases, for some exponents, you can also assume that Ci is negative, which makes the pressure actually a non-monotone pressure. And the structure of the elasticity operator, I'm not an expert of that. I don't know much about that, but it's detailed in this book by P. Sierle. And I'll just talk about the most bad term in terms of compactness. So there is a term of this form, which looks like grad square eta times grad square eta, where it is the structural displacement, and h is the thickness of the structure. And then there are other terms which are not so bad in terms of the compactness. And this elasticity operator is defined with the test functions B, but they're from W2 P slightly greater than 2. Okay, and it should be clear from the rest of the talk that why this term grad square eta times grad square eta is so bad in terms of compactness. Now, writing the weak formulation of the momentum equation is similar to the compressible fluid without structure. The difference appears here that there is the sum of two densities, and also unlike the compressible fluid without structure, here you have terms both from the fluid as well as terms coming from that structure. And the point is, I mean, we used the choice of these test functions for the fluid and structure. It's a bit special because we don't want to see the singular pressure appearing at the fluid boundary. So it's hard to talk about the trace of this kind of pressure because they're just integrable and there is not much information available about their derivative. So we take test functions for the fluid such that the trace function, trace of this test function equals, sorry, it's here, such that the trace of the test function for fluids equal the test function for the solid at the interface. And that by trace here I mean that it looks something like that, the trace of phi. So I mean it looks like phi restricted on the interface eta, but it's not exactly because phi is a fluid test function. It operates on vectors, but it in our case it's just a scalar because it's a graph setup. So what we need to do, we need to take some lifting of this eta to make sense out of this. But I avoid to say that here because I don't include the suitable notations to define this quantity. And simply because we have this continuity of test functions at the boundary, it means the regularity of test function for the structure depends on the solution eta itself. And that's why if we choose test function for the fluid which is smooth, still we cannot get smooth test functions for the solid. It should always be restricted, and the regularity of the test function for solid, it will it's almost be equal to the regularity of the solution eta. So it can be here L infinity W22 intersection W1 infinity L2 function. And now with this, we can state the main result of our article, which has two cases. The first one, when the adiabatic exponents, the maximum of them is greater than 2 and the minimum is positive. We have the assumptions that the initial densities, they are non-negative, but they are not identically 0. And the initially rho 0 is L gamma, Z0 is L beta, and initially the momentum is in L1 on the structural displacement in W22 and the structural velocity is in L2. And case 2, which extends the exponent of the first case from greater than 2 to greater or equal to 2, but the minimum is always positive. And for the second case, we need a slightly extra assumption compared to the case 1. So we will not just assume that the initial structural displacement is in W22, but slightly better, W2 plus sigma 0, 2, but sigma 0 is just a small positive quantity. And with these assumptions, we have the main result of our article, which is the existence of weak solutions in both the cases. And the existence is an existence results is stated in terms of this alternative. So the final time of existence is either infinity or it's finite, depending on the structure approaches a self-intersection, which means a loss of injectivity of the structure. Or the second case, the Quieter energy degenerates. It actually means that the W22 coercivity of the Quieter energy degenerates with time. And this situation appears because we have non-linear and non-convex Quieter energy. So either we have the global existence with finite time infinity, or we have a finite time existence with this avoiding the self-intersection or avoiding the degeneracy of the Quieter energy. So how do we prove our result? It's done in several steps. First, the regularization of Quieter energy and addition of structural dissipation. Then approximation of initial conditions, pressure, and viscosity coefficients. This approximation of pressure is quite standard for the compressible Navier-Stokes equation. And then we extend our problem from a time-dependent domain to a time-independent one, and solve it by a decoupling penalization method, and finally passing the regularizing parameter to 0 and arrive a solution to the physical domain. But I'm going to explain all of these steps, and it's, particularly why do we need this regularization of Poitras energy and the addition of this structural dissipation. So what I mean by extension of domain, it means we don't solve our problem anymore in this time-dependent setup, but we extend our formulation to a time-independent large domain and try to solve our problem in this fixed big domain, and then to come back from this large domain to the time-dependent setup. So for that, what we do first is we extend the initial densities by 0 outside this time-dependent domain. And with this continuity of velocities at the interface of the fluid and structural velocities, we are going to guarantee that if initially we assume these densities as 0 outside this time-dependent domain, then they are 0 for the entire space-time cylinder. And this property of the continuity equation is motivated from the paper of Pyraizel, Kreml, Nesesova, and Nestuba, published in ZDE in 2013. So if we talk about strong solutions, the idea simply is, okay, you have this characteristic race here, which carries the information of density. If you have this continuity condition, this characteristic race never enter your time-dependent domain. So if you initially have 0 initial density here, it's always carried outside the time-dependent domain, and you always get for the entire space-time cylinder that your densities are 0 for all times. But for the proof of this kind of lemma, we need this regularity of eta, which says we need eta to be W12 over the entire space-time cylinder. But this information is not available from the a priori energy estimate for eta. And for that, we need to add one artificial dissipation for now, which is of this form, some parameter delta times time derivative of Laplacian eta. And this is exactly what is going to provide us with this missing information that eta is in W12. But for now, later we are going to have a priori estimates independent of this regularized parameter. And then while proving this density to be 0 outside the physical domain, it's so important, because whenever you have the density 0 outside your physical domain, it simply means your convection is 0 outside this physical domain. So even if you are working in a big time independent domain, implicitly what you have, the density is 0 outside this time dependent physical domain, and at any time you want, you can come back from this non-physical domain to the physical one. Yeah, but this luxury is not available for other terms in the momentum equation. For instance, when you consider this stress tensor part, you don't have any density appearing here, so this thing is not going to help. But what we can do, we can approximate the viscosity coefficients in such a way that at the limit it equals the physical viscosity mu in your time dependent domain, and it's 0 outside that. And that's going to give us that at the limit, this term corresponding to the weak formulation of the stress tensor, it vanishes. So we can pass limit also in the stress tensor term. And the last one, the pressure, and because the pressure is 0, whenever the density is 0, it can simply be handled in the way the density was handled, because it's also 0 outside this physical domain. Okay, so here I didn't want to write all these equations, but I just want to point out a few things from that. So now we are in this time independent setup, and we want to solve our problem. So what we do a time splitting with this tau greater than 0. So you do this time splitting in this small with this small tau, and then we try to decouple the fluid and the structural problems, and we will solve the structural subproblem and the fluid subproblem separately. So for that, we start with the known functions un and eta n, and in the structural subproblem, we solve for eta n plus 1, and putting this n plus 1 in this fluid subproblem, we solve for the fluid velocity at n plus 1th level, un plus 1, and also the densities. So I don't include the continuity equations here, but it can be done in a similar way as that of this momentum part. We can recover rho n plus 1 and z n plus 1. But something we can notice that even if we are discretizing in time, we are not actually discretizing the time derivative. What we are doing is solving evolution equations for small times, and both for the structural subproblem and fluid subproblem. And the second thing, we no longer consider the continuity of velocities at the interface, but rather include such kind of penalization term, which looks like the time derivative of the structural displacement minus this quantity Vn, which is almost like a trace of the fluid velocity, and it comes with this parameter tau. So we can imagine if this tau goes to 0, then at the limit we are going to recover the equality of the structural velocity and the fluid velocity at the interface. But everything needs to be done with something similar to similar like the energy estimate. Then how do we solve this structural subproblem and fluid subproblem? As I was saying, there is already some paper in the literature by Novotny and Pokorny, and they deal with the strong solutions of compressible multi-component fluid model in a fixed domain. So we can use their result, not directly because there are minor changes we have, because we already have approximated the viscosities, but in this paper they considered constant fluid viscosity. And also we have these penalization terms appearing in our equation. So there it needs to be modified, but this modification is really minor. And for the structural subproblem to solve, we again apply another time discretization at delta t there, where this delta t is much less than the earlier time discretization there tau. And in this small time length delta, we even discretize the derivatives. The usual way of time discretization we apply, which means we solve this structural subproblem, but a stationary one, using the coercivity of the operators, the elasticity operator, and then we apply some Lairest order fixed point argument to have the solution of this stationary problem. And finally, by defining some interpolants, we pass delta t tends to 0 and recover a solution of the structural subproblems. But the thing which I want to comment here is because we have this term which is bad in terms of compactness, grad square eta times grad square eta. We cannot just use the W22 coercivity of the cell energy to pass limit here, because simply if we have W22 coercivity, we have the eta is in L infinity W22. We have weak convergence of both of these quantities, but we need a strong convergence of at least one. And for now, the idea is we apply, we add an extra regularizer term to the cell energy, but it's just for now, and then we really need estimates which are uniform in this with respect to this parameter delta. So this regularizing term, which is like grad q beta square, it gives the W32 coercivity of the regularized cell energy. So just a comment, because until now we have regularized the cell energy and also added artificial dissipation to the structure. And this makes our structural equation a bit different, and in strong form, it probably can be written like this. The second order derivative on time on Nečas plus the regular this functional derivative over this regularized Poynter energy minus this dissipation term. And in the right hand side, you have the forcing of the fluid in the structure. Yeah, so for now we have solved our structural and fluid subproblems, but in a bigger domain. And in tau layer, so we need to pass tau tends to 0, and for that we use this routine procedure of defining interpolants and obtain energy estimate for the interpolants. And this a priori bounds lets us extract some weak subsequence. We then prove some strong convergence of the subsequence by Opalian's kind of argument and try to pass limit in both the continuity and momentum equation. But as typical to compressible fluid, the difficult part is to pass limit in the pressure term. And now we even have a bit more difficulty because we have the dependence of pressure on two densities instead of one. So as I was saying, the first part of the talk, if you want to prove more compactness for the pressure, the first step is to improve the integrability of the pressure or integrability of the density, and for that we used Bogovsky type operator. But Bogovsky operator can be used for uniformly Lipschitz domains. But here, because from the a priori estimate we just have eta, the structural displacement bounded in L infinity W22, with embeds in L infinity C0K for K slightly less than 1. So the interface is uniformly Holder, but not uniformly Lipschitz. So we cannot directly use this Bogovsky operator up to our interface to produce uniformly bounds on the pressure. But what we can do, we can keep a distance from the interface and take small parabolic cylinders to have the improvement of density, both rho and z, but not up to the boundary, but a bit far away from the boundary. But what happens near the boundary? We need some information near the boundary also. And this missing information can be done following the argument of Peter Kukuczka, who considered non-Lipschitz domains, but not with structure, but just non-Lipschitz domains. And he developed a strategy to prove equi-integrability up to this non-Lipschitz interface by using test functions of very high divergence. And later, this approach was adapted by Bright and Schwarzschild. We do the same, and we get actually that our pressure is equi-integrable until the interface, and which lets us extract weakly convergent subsequence even in L1, whereby bar, I mean the limit of the pressure. But then the question is how to identify this limit. And it's more complicated than the monofluid case, of course, because of two densities. But the idea is to transit from the bifluid case to the monofluid case. So how do? We first define these quantities. S2, which is the quotient of the two densities at approximate level, Z2 and ρ2, and also S, which is the quotient of two densities at the limit, Z by rho. And what we do, we write our pressure which depends on ρ2 and Z2, as first of all, we replace this Z2 by ρ2 S2, so it now has the form pressure of ρ2 and ρ2 S2, and we add and subtract this term pressure on ρ2 S. So S is fixed, it doesn't depend on 2, so you just add and subtract this term. But then we can notice something. If we are able to prove that this difference goes to 0 in some sense, then what we have is tau tends to 0, limit of this pressure is going to be equal to the limit of this new pressure, tau tends to 0. But here S is fixed, so this thing does only depend on one density rather than two densities. So this is a transition from the bifluid case to the monofluid case. So the goal is to prove that this difference goes to 0 in L1 norm. And for that, simply what we do, we write this difference here, and we use the mean value theorem for the second component. So we have this Lipschitz constant dZp times rho tau times S tau minus S. And here exactly comes into use the assumption, because at some point we assume that our pressure is Lipschitz with respect to the second component, and here we use that assumption. The assumption was that this Lipschitz constant or P with respect to the second component can be bounded by some power of the pressure. So at the end, what we have is everything is dominated by this power of pressure power of density rho times S tau minus S. So now, if we can pass this to 0, it will imply that in L1, this guy goes to 0, and this will give us a way to identify the bifluid thing to a monofluid thing. So yeah, what I was saying, once again, I now want to prove that this integral of some powers of density times S tau minus S goes to 0, and this will give us our the L1 convergence of this guy we are searching for. And so this will at the end mean that the weak limit of the pressure, the original pressure, is going to be the weak limit of this new pressure. And this new pressure is just a function of one variable R, because S we already have fixed. Yeah, so the goal is to prove such a convergence. And how to do that? It was first done for fixed domain by Sourav and Novotny. So it's something we call almost compactness argument, which means we prove by using just the properties of continuity equation that limit of this integral rho tau times S tau minus S to the power P is 0. And I mean, we prove a version of this inequality which is applicable to the moving interface, both for Lipschitz and Euler domains. And so if we have proved this, which means we have identified the pressure of bifluid model to the pressure of a monofluid model. So now everything goes like the monofluid model. So you can identify the pressure simply by using compactness arguments, which are already known for the monofluid case. So I don't comment more about that. But what I want to comment that if we recall, this elasticity energy has some terms of the form integral grad square eta times grad square beta. At some point I was talking about that because they are bad terms, and we got rid of that, or got rid of the problems with the compactness by regularizing the cell energy. But somehow we need to put uniform estimates with respect to this regularizing parameter. So we need to prove that this eta is bounded in L2W2 plus sigma star. Sigma star is slightly greater than 0. And because we already have some information on time derivative, by using this, we can use Opalion's kind of argument to prove the strong compactness of grad square eta. So there will be one strong convergence, and that will let us pass a limit here. This was an idea developed by Sourav and Muha to improve the regularity of eta by using test functions for the solid of this form, which are difference quotients with and difference quotient minus h, difference quotient plus h, operating on eta, and this difference quotient looks like that in these tangential directions, E alpha. So it's like the difference of eta in this tangential difference with eta y divided by h to the power sigma. Sigma is this extra exponent which is going to appear here. So very roughly, if we are able to test the structure equation with this test function, it's going to give us the integral of grad square with difference quotient operating on n whole square And as we pass h tends to 0, it has a contribution of grad square 2 plus sigma on eta. So it will give us the L2 W2 plus sigma norm of eta here. And then again, as I was saying, this improved regularity on the structure plus some information on the time derivative and classical polynomials is going to provide us with a strong convergence of eta in L2 W2 plus something and with integrability 2. Yeah, one more observation. It's so still now we have the extra integrability of eta, but in this kind of space, L2 W2 plus sigma star 2. But if we take the initial structural displacement, which is slightly better, so just not in W2 plus sigma 0, then we claim that eta is actually in L infinity and Lipschitz space. It's because of this Gelfand triple. So we can have this extra integrability W2 plus sigma star 2 and embedded into W2 plus sigma 0, where the sigma 0 is slightly less than sigma star, but still positive. And that can be embedded into the dual space of the first one. So using these three as Gelfand triple, we are able to improve the regularity of eta uniformly in time and W2 plus sigma 0 2 in space. But again, we need for that this extra integrability, extra regularity of the initial structural displacement. So at a glance, what we have two cases. If we have initial structural displacement in W22, the structural displacement for this space-time cylinder is in L2 Lipschitz space. But not L infinity Lipschitz, of course. But if we have this extra assumption on eta 0, that W, it belongs to W, to this semi-spring, so it should be W2 plus sigma 0 2. Then eta lives in L infinity Lipschitz space. And these two things are going to influence our existence result in two ways. The first one, when this adiabatic exponent greater than 2 and eta 0 is in W22. So in this case, as we have seen, eta is in L2 Lipschitz, but not L infinity Lipschitz, but rather L infinity Helder. So in other words, eta is in uniformly Helder. And in this uniformly Helder domains, for the if we want to apply Korn's inequality, which is the main tool to recover the regularity of the velocity from the estimates of the stress tensor, then in uniformly Helder domain we have a bit less regularity in space of the velocities W1q rather than W12, so where q is slightly less than 2, and this means we need gamma greater than 2 for the proof of renormalized continuity equation, which is a consequence of Friedrich commutator argument. Because for Friedrich commutator argument, we need either u is in L2W12 and rho is square integrable, or if we have u in W1q with q less than 2, then rho should be better than just square integrable. So the conclusion existence result for gamma greater than 2 with the initial structural displacement in W22. And the second case, and the last slide. So if we have gamma equal to 2, so it's a slight improvement with the assumption that the initial structural displacement is in W2 plus something with integrability 2, then eta is in L infinity Lipschitz, and which means uniformly Lipschitz, and there is no problem to apply Korn's inequality, the classical one, to have u is in L2W12. And this means for gamma equal to 2, it's enough for the proof of renormalized continuity equation. I mean, we can just use this integrability of rho to be square. We can just use rho to be square integrable with u in L2W12 to prove this renormalized continuity equation. And then the conclusion is existence result for the case gamma equal to 2 with slightly better assumption on the initial structural displacement W2 plus just not in W2 plus something at the boundary. And this was the end of my talk. Thank you for your attention.